All right, let's go ahead and talk about piecewise functions today. Up at the top, I defined it. A piecewise function is a function that consists of multiple subfunctions, with each being defined over an interval of the main function's domain. So what does that mean? So if you take a look at this graph that I've presented for you, we have a piecewise function that consists of two linear functions, one that has an open point and going down and to the left, that's a line, and then a filled in point for my other function that's going down and to the right. So when I go to write a piecewise function, I'm going to use our function f of x equals, and then I'm going to use a curly brace, and that curly brace is going to denote the two separate functions individually. Now, since both of these are lines, we know that the equation of a line is y equals mx plus b, where m is my slope, b is my y-intercept. So looking at the first graph at the bottom left, we can see that I have a slope of up 2 over 3. So I'm going to write f of x equals 2/3 x. My slope is positive 2/3, and my y-intercept is at -1. Now notice that that graph doesn't go on forever. It's restricted, and we're restricting it based off its domain. So we want all values of x that are less than 0. And the reason why we're using less than is because, again, that point is not included at 0, -1. And then for the function above, we have a slope of down 1 over 1. So we have a slope of -1, so -1x, and my y-intercept is at +3. And this one is included, and it's for all values greater than or equal to 0. So that would be my piecewise function. Now, from an algebraic standpoint, in this next example, you can see that I have another piecewise function that includes three separate functions. The first one is 2x plus 8, which is linear, x squared minus 3, which is quadratic, and the third one is the square root, which is the square root of x plus 3. And for each one of those functions, it has its own domain restrictions. Now, for the first part of this, it's asking us to evaluate f of -4. So I'm asked to input -4 into this piecewise function. The only thing is, I have to know which one of these three functions do I actually plug -4 into. To figure that out, you have to look at these domain restrictions. And I have to see which one includes the value that I can input for x to be -4. And it just so happens that the only one that includes -4 as part of its restriction is this top one. So I'm going to take 2x plus 8 and evaluate it when x is -4. And I get -8 plus 8, which is 0. So when I input -4 into this piecewise function, my output is 0. Next one is f of 6. Which one of these three functions does it include x being 6? That would be the third function. The square root function is square root of x plus 3. I'll substitute 6 in for x. And I get square root of 9, which is 3. F of -2, the only function that includes -2 is the first one. So 2 times -2 plus 8. -4 plus 8 is 4. And then 0, based off my domain restrictions, it's the middle one. So I'm going to plug 0 in for x into that quadratic. 0 squared minus 3. 0 minus 3 is -3. All right, go ahead and spend a few minutes trying this try it section. All right, moving on to this example now. We have a new piecewise function that contains three individual functions, a cubic, a linear, and an absolute value. We're asked to evaluate f of 8. So based off my domain restrictions, we can plug 8 into our third function, which is the absolute value. So absolute value of 8 minus 2 is 6. Absolute value of 6 is 6. Again, remember, absolute value represents the distance away from 0. So absolute value always comes out to be a positive output. Now for 0, which one of these three includes the input of 0? That would be the first one. 0 is less than 1. So I'm going to plug it into my cubic function. 2 times 0 cubed minus 1. Order of operations, I'm going to take 0 and cube it, which is 0. 2 times 0 minus 1. Multiply 2 times 0, I get 0. Subtract 1 is -1. F of 4, I can plug it into our middle function. Now notice for the middle function here, I'm going to circle this. No matter what I plug into my function, As long as that domain restriction is satisfied, my output is always 3. All right, so f of x equals 3 simply means that any value I plug in will always give me out an output of 3. And then for 5, I'm going to use our absolute value function. 5 minus 2, absolute value of 3 is 3. All right, from a graphical standpoint, we can evaluate these functions the same way. So starting with f of 2, I'm inputting 2 into my function, so what is my output? At 2, we get out -1. At -3, we get out 2 values, one that's included and one that's not included. We're, of course, going to use the one that's included, which is 2.5. At -1, notice we have 2 points, both of which are not included, so we're going to say it's undefined there. There is no output when my input is -1. At -4, I get out 2. And then for our next example, when I plug in 0, I get out 2. When I plug in -4, I get out 1. -1 gives me out 2 points. Again, we'll choose the included one, which is -2. And then at f of 3, when I plug 3 in, I get out 3. All right, go ahead and try it section, and I'll come back in a few. All right, let's go ahead and come back together. For the try it section, I have 2 functions. Let's start with the top one, -2x plus 1, where x is less than 0. So I'm going to start it where x is 0. My y-intercept is 1. That's going to get an open point since we're not including the x value of 0. And then my slope's -2. So I'm going to go up 2 over 1, up 2 over 1, up 2 over 1. And notice that I'm going up and to the left because I only want values for this function where the domain is less than 0. And then for my second function, 2/3 x minus 3, where x is greater than or equal to 0. My y-intercept's at -3. That point is included since I want my domain to include 0. And then my slope is up 2 over 1, 2, 3. Up 2 over 1, 2, 3. Up 2 over 1, 2, 3. Again, notice that I'm only plotting points that are greater than or equal to 0 for x. For my second example, here is a linear function again. We have y equals 5. That's a horizontal line where x is only less than or equal to 2. So I'm going to go to where x is less than or equal to 2. When x is 2, I get out 5. 1, 2, 3, 4, 5. And it's included. And then it's all values smaller than or equal to x being 2. And the next one, we got 2x minus 4, where x is greater than 2. So the y-intercept's at -4, 1, 2, 3, 4. I got to go up 2 over 1, up 2 over 1, and I'm going to start where x is greater than 2. So I'm going to have an open point here, and then continue with my slope, up 2 over 1, up 2 over 1, up 2 over 1. And again, notice that this graph in red represents the function y equals 2x minus 4, where x is greater than 2.